So today's lesson has an objective that might sound familiar to you. The first part of today's lesson, we're going to be deciding whether relations represented verbally, so like a word problem, tabularly, graphically, or symbolically define a function. Let's highlight some important words here. One of the most important words today is function. That's what we're going to be working with today. And the one thing I really need you to know how to do is that whenever you have a function, it means that none of your x's are repeated. So a function, what you can remember is repeat x's are no fun. In math and in real life, you probably shouldn't repeat your x's because that's no fun. So we're going to do the same thing for these functions. Now we're going to be able to tell if y is a function of x for graphs and tables, mappings, and points. When we're looking at a graph to decide if something is a function, we employ something called the vertical line test. Does this sound familiar to anybody?
No. A what?
A vertical line test.
Yes.
Okay, it should. This should sound familiar. You would have maybe done this before. In a graph, if something is a function, you can draw a bunch of vertical lines across your entire graph. And notice that those vertical lines only touch the curve, only touch the function once each time. That's a function. But if you look at the second example here, if you draw a line, and go ahead and draw a line through it, how many times does that vertical line touch this graph? Twice. Twice. If it touches it twice, it is not a function. Super easy to tell on a graph if something is a function. If any vertical line touches that graph more than once, it's not a function. From tables, mapping, and coordinate points, it's really easy as well because all of those things give us a list, essentially, of the x values. So all we have to do is check for the repeating x values. And if any of your x values repeat, then it is not a function. So if you look at that first table, 6, -6, 8, and -8 are my x values. Did any of those repeat? No, none of the x's repeated. I don't really care about the y's, so even though some of them repeated on the y list, don't care. We're looking at the x list. None of them repeated, so it's a function. In the second one, in this mappings are just like collections or pictures of coordinates. If you look at that very first thing, we have 3 going to 2, and then 3 going to 6. That's not a function because it's like the coordinate 3, 2 and 3, 6. You see that x is repeated? Not a function. Still a relation, but not a function. Yes? So let's do a couple example problems of the different variety we might ask you. So a function, remember, is a set of ordered pairs that has one output for each input. Basically, don't repeat your x's because repeat x's are no fun. So I'm going to ask you, is y a function of x? We look at only the x coordinates. In that first list of ordered pairs, the first row, do any of the x values repeat? Yeah, right here. Remember, x values are the first part of a coordinate, x, y, so we're looking at the first part of these coordinates. Since those 1 values repeated, we'd say y is not a function of x here. In the second list of ordered pairs, do any of the y's repeat? Y's. Nope. Do any of the x's repeat? Yeah, literally all of them are repeated, so this is not a function. But in the third one, do any of those x's repeat?
No.
So it is a function. The y's repeat. Do we care that the y's repeat? No, we don't really care about the y's. We just have to make sure none of those x's repeat. If they're all unique, which means they're all individual, then it is a function of x. What are our questions before we move on?
Were we supposed to learn this last year?
We did. This was something you probably did learn last year, and you either forgot or didn't, so that's okay. I'm teaching you now. No worries. Let's look at these mappings. Now, me personally, I have a hard time looking at mappings and following the arrows, so I actually list out the coordinates. And I suggest you do the same, especially while we're learning. That first arrow goes from -2 to 18. So that's my first coordinate. The second arrow goes from what number to what number? 0 to 1. So that's my coordinate. The next one goes from 8 to -7. And the last one goes from 9 to 1. Is y a function of x? Why do you say yes? No repeating on the x. Do I care that the y is repeated? Nope. There is no repeating on the x's. These are all unique or sorry. So all of them are unique. Sorry, I just lost my train of thought. This is a function of x. I want you guys to do the next one. If you need to list out all of the coordinates, I suggest you do that. But is y a function of x for that mapping? All right, what are we thinking? No. Great. Okay, why is it not a function?
Because the x repeats.
The x repeats for 0 and 1. Yeah, if I wrote these down, this would be 0, 0, 0, 12. Already I can tell it's repeated. So no way, y is not a function of x if those x's repeat. Make sense? Okay, flip it over. We've got a couple more representations here, so a couple more ways that I might show you functions. And I still want you to be able to tell me if y is a function of x. We got these tables. I love tables because they're nice and organized. In that first top left table, is y a function of x? No, why not?
Because the x repeats.
The x repeats. This value of negative 0.2 repeats. For the second one, is y a function of x?
Yes.
Yes. Are any of the x values repeating?
No.
No, we're good. They're all unique, which means this is a function of x. Y'all got the next two tables, please. Okay, what did you get for the first one? Is y a function of x?
Yes.
It is.
It is. None of those x's repeat, so we're good to go. In fact, that's the same table from the front side of these notes. What about the second one? Is not. Which x value repeats? Negative 1. So it is not a function of x. Cool, great. I love tables. They're just organized coordinates. Graphs are also really fun because now we're still looking for repeated x's. And the way that we do that is with that vertical line test. One thing that I realized in some of my classes that's confusing is when I'm talking about the graph, I'm talking about the curve or the squiggly line or the wave or the circle. This is what we're trying to test and see if any vertical line crosses more than one time. I'm not talking about the x and y axis. I'm talking about the function drawn on the coordinate plane. Okay, so when we employ the vertical line test here, I'm going to draw a bunch of vertical lines through this graph. Do any of those vertical lines ever touch that graph more than once? No, so this is a function of x. But if we look at the second one, I draw a vertical line, even just one vertical line. Look, how many times is it touching? Twice. Is that a function?
Yes.
Oh, if it touches twice, it is not a function of x.
Oh, I got them confused. I put it's not for the left one and it's for the right one.
Yeah, so if it touches it twice, it is not, because that means we've repeated that x value. I want you guys to do the other four that are left. Tell me, is y a function of x? Okay, let's go over these. I think we have enough time. The third one on the top, is y a function of x?
Yes.
Yes. All of my vertical lines only touch that green curve once. What about the bottom one?
No.
No. Any of the lines I draw, pretty much all, whoa, it is not a function. And then this one, middle, is that a function? No, y is not a function of x. And then this last one, I'm going to zoom in so you can really see this. But if I draw some vertical lines, some of them are fine. But what happens right here? How many times does it touch this graph? So is y a function of x?
No.
No. Even if that happens just one time, it means it is not a function anymore. It's just a relation.
Wait, this one is.
So an extension question I might ask you, and this is pretty cool. Luke is constructing a table of values that satisfies the definition of a function. Highlight the word definition of a function. We just learned what that is. What is the definition of a function? No repeating what? No repeat x's. Okay, so we know that that's the definition of a function. It says which numbers can be placed in the empty cell so that the table of values satisfies the definition of a function. There's two correct answers. I don't want you to say anything. I want you to think. Look at these answer choices. There's two of them that I could put right there so that this was still a function. I want you to find them. Okay, I'm seeing really good things as I go across the classroom. So can I put a -5 right here? Yeah, because is -5 make me have any repeating x's?
No.
No, so this one is one of the things I can pick. Can I put a -1 right here?
No.
No, because that makes me repeat, right?
You can put in 2.
I could put in 2? Okay, I'll get there. Let's check 0 though. Can I put 0 in there?
No.
No, because that makes me repeat again. Okay. And now let's get to 2. You already said it's in there, but let's check. Does that make me repeat anything?
No.
No, so that is one of the numbers I can use. So obviously 11, I repeat with 11. It's right there. So that's also a repeat. So the 2 numbers I can get in there so that this still satisfies a function, meaning none of the x's repeat, are -5 and 2. How do we feel about a function or not?
It's really hard.
It's really hard.
If this is what's gonna happen, it's gonna.
This new part of this lesson,
She's like, nah.
in this new part of this lesson, it's called function notation. This is going to become really handy for you in the higher level maths you get to. Our objective of the day is to be able to evaluate functions expressed in function notation given one or more elements in their domains. Your important words here I want you to highlight are function notation. And then don't highlight it, but I want you to circle the word evaluate. We've used the word evaluate before, and you've probably seen it before. Does anyone remember what we do when we evaluate something in math?
No.
Examine it. Love that. No, actually, we're going to plug in a number, and then we're going to calculate or solve. We're going to plug in a number, and we're going to calculate. That means we're evaluating a function. So quick review. We just defined this. A function is a relation in which each domain, x value, corresponds with exactly one range, y value. Basically, the x's don't repeat, right? That's the mathematical way to say that. But what's going to happen is in math, we're going to start talking about more than one function at a time. And so let's say I have the functions y equals x plus 3, and then I have y equals x minus 5, and I have y equals 2x plus 1. It gets really confusing when we're dealing with more than one equation at a time. You can't always say the top equation, the bottom equation, the middle equation, because what if I wrote them side to side? The left one, the right one, the middle one. It's confusing. So we have this method of notating these functions, and it's called function notation, that allows me to describe a very specific functions. The way that we do this is we change the y value, the output, and we put this symbol or this grouping of symbols here. We get to pick the name of the function. So I'm going to erase all these y's, and we're going to name all these functions. I'm going to name the first one f. What letter is plugged into f? Okay, so we're going to call this f of x. Great. The next one I'm going to call g. And what letter is plugged into g? The last one, because I'm selfish, I'm going to call q. And what letter is plugged into q? Of x. So what we are doing is we're allowing ourselves to do 2 things. Number 1, we have now named the functions. I can refer to them as f, g, and q. Not top, middle, and bottom, but I actually gave them a name. The second thing, and what this parentheses is, I'm not multiplying these like typical math notation. This is function notation. It is pronounced, I want you to write this down, f of x. Don't say f times x, don't say f parentheses x, it's f of x. If I change the letters, like g of x, I just change what I'm saying. Q of x. Okay? This is just a naming system. The number in the parentheses or the letter in the parentheses should match exactly what's in the equation. So if I did this, I'm going to erase the x out of g, and I'm going to change the letter inside g to a t. What should now go in this parentheses?
T.
A t. Let's say, again, because I'm selfish, I'm going to keep using my initials here. If I change the x's in the q function to a k, what should go in the parentheses? A k. That's now called q of k. So this is just telling me what I've plugged in and the name of the function. It allows us to talk about more than one function at a time. Okay, so here's a few examples for you. You've got f of x, h of t, c of n, where they have the name of the function, what's being plugged in, and what we get out of it. Let's try rewriting some things in function notation. So we have this equation, let's highlight it. Y equals 2x plus 4. That represents a function. I want you to rewrite y equals 2x plus 4 using function notation. And you can be selfish for a second. Name the function using the first letter of your name.
Oh, that's why you put Q, because your name is quickly.
Yeah, yes, I'm selfish for a second. So use your first name, your first letter of your first name, and name this function. So if I was doing this again, my first name starts with a K, so I would say K of x equal to 2x plus 4.
My name starts with the X though.
Oh, I'm so glad you said that. Look at this next thing. It says, does anyone in your class have a name that starts with X? Why did you pause and say that?
Because it's already an X.
Yeah, this is what Xavier's would be. Isn't that confusing? Yeah, so there's a few letters we don't use when we do function notation. Yeah, we're not going to use X's, we're not really going to use Y's, and we're not really going to use Z's, because those are variables that you'll use. The X and Y and Z planes. Z is not till algebra 2.
I'll just put my middle.
Perfect, love it. So try to avoid the X of X, that's weird. Y of X and Z of X, it's just weird. And we just don't do it. It's confusing. But if you wrote down for Will, W of X equal 2x plus 4, that's it. You have now named that function W and told me that I'm plugging in X's. Easy, right? So the main reason that we do this naming of functions thing is so that we can evaluate functions better. Flip over the page. If you look on this side, this is really why we do this. Since the function notation f of x relates the inputs, the stuff in the parentheses, and outputs of a function, it can be used to indicate how to evaluate these functions, which is one of the things that we want to know how to do today, evaluate a function. So let's look at an example. This is when I blew everybody's minds during second period, so just stick with me for a second. Here's the example. It says, if g of x is equal to 5x minus 2, so we have an equation. It says, what is the value of g of x? Oh, sorry, g of 6. Okay? 1 second ago, my function notation said g with an x plugged in. That's what this right here says, g with an x plugged in. And then all of a sudden, it says to do g with what plugged in? A 6. Okay, no big deal. Guess what I'm going to do? I'm going to plug in a 6. So instead of x, I write 6. Instead of x, I put a 6 in parentheses. I've plugged it in.
Because of that, are you going to multiply?
Absolutely. What's 5 times 6? What's 30 minus 2? I'm done. You've evaluated. You've calculated. Even so, my friends, you don't even need to actually do this part in your head. I want everybody on their Desmos right now to type just the right side of this equation in. Maybe your calculator if you're not a Desmos person, but 5 parentheses x minus 2. I want you to type that in and make sure you get 28 out. Yeah, when we throw 5 parentheses 6 minus 2 in the calculator, yeah, I can do it in my head. That one's pretty easy. But when they'll get more complicated, we're going to turn to our calculators to be able to evaluate this, and we don't make any mistakes because we've calculated it in a calculator. Does that kind of make sense? Let's do a couple practice problems together, and then I'm going to let you try on your own. This first one, example 1, says, given p of n equal to 1/2 n minus 5 squared, what is the value of p of 9? What am I plugging into p? 9. So, okay, so instead of n, everywhere there used to be an n, I'm going to put a 9 in parentheses. So there's an n, and then here's a 9, it goes in parentheses, minus 5 squared. Does that make sense? We've just plugged in that 9, plopped it into the equation wherever the letter was a second ago. Here, wrong color, here and here. At this point, don't do anything extra. In your Desmos or in your calculator, toss the right side of that equation in. Go after the equal sign where there's only numbers and type in 1/2 parentheses 9 minus 5, close parentheses, squared. I'll show you on my screen because I know that's a whole lot of buttons. We might not know where they are. Hold on. We would evaluate it, and I already forgot what we just evaluated it to. What was it? 8. Thank you. So P of 9 is equal to 8, and we would be done. That's why we do function notation, because we're going to be able to plug numbers in really easily and have inputs and outputs shown in function notation. Okay, number 2 is right underneath it. I want you guys to try number 2. So one right underneath it. Okay, so here's something that I want you to see, and I think I'm seeing this kind of widespread. On number 2, we have f of x, and what am I plugging into f of x? Great. Let's make sure we plugged this in right. So we're going to do f of negative 2, which means anywhere I saw an x previously, I'm going to put a negative 2. If some of you are like, wait a second, you've got a double negative, Miss Quigley. That's correct. Minus a minus is what?
Positive.
Positive. But Desmos is smart enough to calculate that for you. So if you want to rely on Desmos to do that calculations for you, you can just go ahead and plug that in. Let me show. So what we would have gotten that f of negative 2 is equal to 28. Voila. Yeah, so wherever your x or your t or your n value is, that's where you're going to plug it in. So look at number 3. How many t's are in that equation? 2. So how many times are you going to be plugging in 10?
2.
Okay, I want you to try it. Give it a shot. Okay, if we started number 3, we'd have h of what number? What am I plugging in?
10.
10 equal to everywhere that was a t now becomes a 10 in parentheses. Exactly where it is.
Can I start on 4?
If you toss all of that into a calculator, making sure you did give me a decimal and a negative, you'd have gotten that h of 10 is equal to negative 240. Is that what you got? Woo-hoo. Nice. All right, my friends, so what am I plugging into the c of n function? 5. So this is going to be c of 5, which means anywhere there was an n before, there's now going to be a 5 in parentheses. When you toss all of that into a calculator and evaluate, we should get that c of 5 is equal to 37. How'd we do? The only way that we could possibly try to make function notation harder is a way that makes it more realistic. This is a way that we would use function notation in real life. Okay? Let's say you own a grocery store. You are the manager of a grocery store. And you studied your store to discover things about your business, because that's what business people do. And you realize that the number of bananas remaining on the shelves at my store can be determined by this function, b of n equal to 150 minus 6n, where n is the number of hours since the store opened. B stands for bananas. N stands for the number of hours since it's opened. The question here is, how many bananas are left on the shelves after the store has been open for 6 hours?
So is it going to be replaced with 6?
Very good. So we're going to figure out how many bananas are left when I have already been open for 6 hours. This is function notation in real life. I'm plugging in the 6 because I've been open for 6 hours, and n is my number, n for number of hours.
I should have went to the restroom right now.
So how many bananas do I have on my shelves after 6 hours?
114.
114 bananas. That's it. That's how many bananas I have left in my store. Good to know in case I was doing stockpiling or I was trying to take an inventory. These are things that business owners have to know. I want you guys to try example 6, the train problem. Okay, I hear some people are finished, so let's get started. Train conductor determined the distance in miles a high-speed train was from its destination using distance of hours, so d of h, equal to 1,375 minus 110h, where h is the number of hours traveled. How far is the train after 8 hours? So we're going to plug in what number to this function?
8.
8. So instead of an H for hours, we're going to have an 8 for 8 hours. So we would calculate that. We'd throw that into a calculator. 495, that's how far it is. I guess, yeah, it told us miles. 475 miles away. Very nice. Okay, we see how function notation works. We're about to play a game with function notations. Are there any questions before we go?